So we're going to look at this concept of continuous functions on closed intervals. The first thing we need is the definition for one-sided continuity. So let's start out with a picture. And let's think about x equals a. And we want to think about what it means if we're continuous, but only coming from the left side. And so remember, the idea of continuity is that the function value, if we had the function drawn like this, it would be that the function value at a, f of a, equals the limit of f of x as x approaches a. But in this case, we don't care about the right-hand side. We only care about the function value at a, so this being f of a, and the one-sided limit from the left equaling f of a. And that's exactly this condition here. So this is an illustration of the idea of f being continuous from the left at a. So the function evaluated at a matches the limit as x goes up to a from the left of f of x. Similarly, we have a definition of continuity from the right at x equals a. So in that case, you just reverse the picture, and now we're coming in on the right. The limit from the right equals the function value. So the limit from the right as x approaches a of f of x, that limit is the same as f of a. That's our continuity from the right condition. When we put both of these together and we look on a closed interval AB, if we're continuous from the left at B and continuous from the right at A, this is what it means to be continuous on AB. This picture here. Now, intuitively, you can think of that as you put the pen down at f of A, you draw the graph without taking the pen off the paper, and you end it at f of B. And so I should also mention, continuity on AB means continuous from the right at A, continuous from the left at B, and then the regular notion of continuity in between, for all the x in between. This is a very important situation because in applications, also further in math, but in engineering, science, all different kinds of fields, the idea of a function on a closed interval is a very natural thing. If you think about maybe a manufacturing plant that has the ability to use so much of different resources, typically you have some lower bound, probably 0 for a minimum amount of some resource up to some maximum amount, and you might be doing something like having a profit function or a cost function as a variable of that input. Point being, that function is usually continuous, and it's typically very natural that you're working on a closed interval. For instance, if this manufacturing plant, say, they're making cell phones and they're looking at some function of an amount of some trace element, well, you wouldn't be looking on the whole real line because you wouldn't have an infinite amount of that element. It would be some amount between 0 and some positive finite value. So this situation comes up a lot. As an example, this is f of x is the square root of x, and this would be an example if we're confining ourselves to the interval 0, 9. And so this function is continuous for all the values between 0 and 9, and then there's no issues here at 9. We have continuity from the left. The limit as x approaches 9 from the left of root x is 3, which is also f of 9. Similarly, here we have continuity from the right at the origin. So this is an example of a function that is continuous. So f is continuous on 0, 9. And so remember, besides the continuity from the left at 0 and the continuity from the right, from the continuity from the right at 0 and from the left at 9, having regular continuity in between 0 and 9 means no jumps, no holes, no vertical asymptotes. Okay. And maybe we can label this here. This is 3. Yeah, so we can be explicit that the limit as x goes to 9 from the left of root x is 3, which is also f of 9, which is root 9 or 3. Similarly, as x approaches 0 from the right, the limit of root x is 0, which is also f of 0. So we see this gives us our continuity from the right, the continuity from the left at this right endpoint, and here we have the continuity from the right at the lower endpoint. A very important theorem in calculus is this intermediate value theorem. So suppose f of x is a continuous function on the closed interval ab, then f of x assumes every intermediate value between f of a and f of b. In other words, if k is such a number between f of a and f of b, then there has to exist some number c in the open interval ab such that f of c equals k. Okay, complicated sounding theorem. But if we draw the picture, it will be much clearer. So we have our interval AB, and we know that, let's say that this is f of A, this is f of B, just as an illustrative example. And we know, because the function is continuous on the closed interval AB, we start at f of A, and then we draw the function without taking the pen off the paper and ending at f of B. So whatever it looks like, we can't take that off the paper. No jumps, no vertical asymptotes, and no holes. So what is this intermediate value theorem? Let's translate this theorem into the picture. So if k is any number between f of b and f of a and f of b. So k is some number over here. What the theorem says is this k has to be connected with some c in AB, such that if you plug c into the function, you get k. So what this is saying is, take this k, now march over. There has to be some point where the function takes a value of k. And we're calling the point where that happens c. And this is specifically because f is continuous on this closed interval. If f was not continuous, this wouldn't necessarily hold. And by the way, you can see how this works. Take this k and slide it up or down between f of a and f of b, and this blue point will just slide along the function. So it'll have some x coordinate that corresponds with it. So as you move this k up and down, this c will move right or left. But there will always be such a c. If f is not continuous, we can see an example of how it would work. So if f is not continuous, example, maybe we're here on AB, and maybe we have a jump. So maybe we have something like this. Here's a jump. Well, in this case, if you chose a k, maybe we should be a little bit more. Here's your f of a. Here's your f of b. If we chose a k here, in that gap, there's nowhere to go. If we move right, we never intersect the graph. There's no c in this interval that when you feed it to f gets you to this level. So in this case, we can explicitly see a visual example of how having a function that's not continuous on the closed interval, you may not have this property. But if you are continuous on the closed interval, this always holds. So let's do two examples. The first one is just an example to kind of give you an intuition for this. So let's work through this idea. Car is driving east through Worcester, Mass on Route 90 on the Mass Pike. And we're going to think about the velocity function of this car. When the car enters the city on the western boundary, we'll say at t equals 0 minutes, so you'd start your stopwatch as soon as you enter Worcester, and it's traveling 40 miles an hour. So let's think about the velocity function of this graph. So we're at time 0, and we're at here. So this is f of z, we say v, our velocity function, v of 0, which is 40. Then the car is driving through the city, and 10 minutes later, it leaves the city on the eastern boundary at 80 miles an hour. So at the 10-minute mark, we're here at 80. So that's the velocity at 10 minutes. So now we'll make the assumption that the car's velocity function is continuous on 0, 10 in that 10-minute interval, which is a pretty reasonable assumption. We shouldn't have a vertical asymptote, otherwise your velocity would be asymptotically approaching infinity. We wouldn't have a hole because you wouldn't have an instant where your velocity would just instantly change and then come back. And we wouldn't have a jump. You wouldn't have an instant where instantaneously you go from, say, going 40 miles an hour to 60 miles an hour. Your velocity function is naturally a continuous function. So the question is, what can we conclude from the intermediate value theorem? And the conclusion we can make is that because of this continuity assumption, whatever this velocity function looks like, we have to draw it by starting here at the velocity at time 0, and maybe you hit some traffic, and then the traffic lets up, and you're going faster and faster, and then the traffic clears up, and as you leave the city, you're going 80. The conclusion is that whatever this plot looks like in between these 2 points, it has to be drawn connecting the dots without taking the pencil off the paper. What that means mathematically, pick any k here, you go over, and there's some time, what we were calling c, at which that value k is attained. Intuitively, for any velocity k, where k is between 40 and 80, there is at least one instant in time, which we'll call c, depicted in orange, where v of c is exactly k, i.e. the car was traveling k miles per hour at time c. So for every velocity between 40 and 80, there had to be a time in that 10-minute window when the car was going that exact velocity. Now notice here we drew it where the car actually went below 40. We can't make that conclusion that, say, maybe here at, I don't know, what's that, maybe 25 miles an hour was the velocity for the car. We can't get that conclusion from the intermediate value theorem. We only can conclude it for all the values between the velocity at time 0 of 40 and the velocity at time 10 of 80. So this is a nice intuitive way to think of the intermediate value theorem. Another example, and this is a pretty standard type of intermediate value theorem example, is we're given an equation and we want to show that it has a solution in some closed interval. Now, in this case, you can, we all know that you would solve this by bringing the 5 to the other side, add 5 to both sides, and x would be root 5. So another way to say this question would be, show that square root of 5 is in the interval 2, 3. So what you might be doing is, imagine this was a more complicated equation. You might be saying, well, we want to solve this equation. Let's get an idea of where the solution is, and then we're going to use some kind of numerical routine to calculate it. Getting an idea of where it is gives us a first guess. So the way we do this is define f of x as the left-hand side up there. And we want to show f has a root in the interval 2, 3. That's the same thing as showing that this has a solution, right? This is f of x equals 0, which by definition is finding a root of f. Well, let's think about this. Let's just plug the endpoints into f. So, checking those, we check the endpoints, first checking f of 2, and f of 2 is 2 squared minus 5, or 4 minus 5, or minus 1. So we know that the function has a point of x equals 2, y equals minus 1. So we are here. Checking the other endpoint, f of 3, gives us 3 squared minus 5, or 9 minus 5, or 4. So we have the point 3, 4. Now, this function is a polynomial. Which means it's continuous. In general, continuous for all the real numbers, and thus continuous on our closed interval 2, 3. Well, intermediate value theorem says any value between minus 1 and 4, and so remember here, minus 1, that's f of 2, and 4 is f of 3. any value between these two, f of 2 and f of 3, has to be attained somewhere in 2, 3. We have to draw this function, whatever it looks like, by connecting the dots in a continuous way. So there has to be a c where this value, this is the k equals 0 case. So we can pick any value between -1 and 4. We pick 0. By the intermediate value theorem, there has to be a point c where that 0 function value is attained. So the intermediate value theorem implies that, more terminology, backwards capital E means there exists. There exists a C inside the interval 2, 3 such that f of c equals 0. And so that c is a root, by definition, of our function, and therefore a solution of our equation. So this is a very standard way that this is used.